Okay, so this is our first, we're going to do an intro into the next chapter, chapter 10, which is talking about linear systems, well, systems of differential equations. Um, so before we get into this, we should review a little bit from 17b because some of these concepts are going to be used here. So recall from 17b, if you had a differential equation, dx dt was equal to some constant a times x. And what that differential equation would be modeling is the rate of growth of x. If x is a population, the rate of growth of x with respect to time is a is a constant, so we would read that as proportional to x. So that's just saying what happens to the growth rate of a population if it's growing at a rate proportional to its own size. Okay, now we spent some time on this in 17b. If you separate the variables, so move the x over here, move the dt over there, integrate both sides. Left side's going to be ln of x. The right side is, remember, a is a constant, at plus c. If we exponentiate to solve for x, remember this trick we thought of as e to the at plus c can be thought of as e to the at times e to a constant. And e to a constant is just another constant, so we'll just replace e to the c with c. And the point I wanted to make here is that is the equation for exponential growth. We should recognize that. So what that then tells us is anytime we see a differential equation of the form dx dt equals ax or some constant times x, we should know now going forward that that differential equation is describing exponential growth or decay. I should acknowledge that. If a was a positive number, then that's talking about exponential growth. But if a was a negative number, like -1 or -2 or -3, that would, of course, be describing a population that's decreasing over time, that's decaying. And that's going to come up. The next thing we want to review is how to find the eigenvalues and eigenvectors for a matrix. This is something we did at the end of 17b, so it should be still fresh in your memory. So if I have a matrix like this, to find the eigenvalues, I'll abbreviate that E values. We're going to do the short story. Remember, you do the determinant of a minus lambda I equals 0. So you take your matrix minus lambda. Remember, I is the matrix with a diagonal of 1s. If you distribute the lambda and then subtract, ultimately you're going to end up with -1 minus lambda, 4 minus lambda, and the off diagonal entries are going to remain the same. To do the determinant, recall we just do the product of the main diagonal minus the product of the off diagonal. That's going to lead to a quadratic formula. In this case, it happens to factor nicely into lambda equals 1 and lambda equals 2. There is, I was acknowledging here, you may have learned in 17b, I underline may, you may not have, and it's okay if you didn't. There is kind of a quick way to get straight to that quadratic formula. We define the trace as the sum of the main diagonal entries, and we abbreviate that tau. So the trace here would be -1 plus 4, which is 3. And the determinant, the straight up determinant, is like we did above, but you're just going to go -1 times 4 minus -3 times 2. And we abbreviate that delta. And what always ends up happening, this quadratic that we had to factor up there always has the form of lambda squared minus the trace times lambda plus delta equals 0. So you could just go straight to lambda squared minus 3 lambda plus delta in this case. And that was the quadratic we solved up above that factors into 1 and 2. Okay, once you find your eigenvectors, then you need to find the corresponding eigenvalues. Now, it's important to note, some teachers will teach this differently. If you had me for 17b last quarter, we know that some teachers did it different than the way I did it. I prefer, I'm a stickler for this. I kind of like to stick with this. I want people to know what an eigenvalue means. And so using my method, it really gets at the definition of an eigenvalue. An eigenvalue means if you take, and an eigenvector, if you take your matrix times a special vector, which we'll call an eigenvector, it's going to just be the eigenvalue times the vector. Okay, so what that effectively means, so for example, if I set lambda 1 equal to 1, if I just randomly call that my first eigenvalue, if I take this matrix times a random vector, this is my eigenvector, I'm trying to figure it out, it's just going to equal my eigenvalue times the vector. So what is that effectively saying? That's saying this matrix acts like a constant, right? That whole entire matrix of 4 numbers behaves like just a single number. And that's actually the magic of eigenvalues and eigenvectors. That's the useful part of it. Now, if you take this equation and just multiply out the first row times v, negative x1 plus 2x2, and that would equal the top number, 1x1. My goal is to just find a relationship between x1 and x2. Oftentimes I can find that just by just doing the first row times my vector, and I don't even have to do the second row. And sure enough here, if I add x1 over to the other side, I get 2x2 equals 2x1. That means x2 equals x1, and that's all the information I need. Because what that's telling me is my eigenvector has to have the relationship where both of these numbers are the same. Now, you can choose any numbers you want. There's more than one eigenvector. The simplest numbers to choose would be 1 and 1, right? 1 for x1 and 1 for x2. You wouldn't want to choose 0 and 0, because even though that satisfies this requirement, it's a non-interesting vector, right? It doesn't go anywhere if you have 0 and 0. Okay, same thing for my second eigenvector. Lambda 2 equals 2. Matrix times vector equals eigenvalue times vector. The first row times my vector gives me negative x1 plus 2x2 equals 2x1. This time when I add it over, I get 2x2 equals 3x1. And if I'm just solving randomly for x2, would equal 3/2 times x1. That's what I needed. I needed a relationship between my two variables. Now, typically, we like to avoid fractions for our eigenvectors if we can. So the best way to choose x1 here is if you let x1 be 2, then x2 is going to be 3/2 times 2. The 2 would cancel, so I would get 2 and 3 for my eigenvector. Again, that's not the only choice of numbers, but as long as this relationship holds, it's a valid eigenvector. Okay, now we get to move on into how we're going to use this in 17C, all this information. I find it's easier to kind of think about this in a context of some problem. Not all of the book problems are this written in context. Let's decide that x1 of t is going to represent our population size of a predator, for example, wolves, and x2 of t is the population of prey, let's say deer. So dx1 dt would represent the growth rate of our predator population, and dx2 would be the growth rate of our prey population. Now, intuitively, since the predator-prey populations, we would expect them to be dependent on each other, right? One affects the other. So it makes sense to study those two differential equations together. And this is the idea of a system of differential equations. Okay, so let's suppose now this is our actual differential equation. dx1 dt equals negative x1 plus 2x2. dx2 dt is negative 3x1 plus 4x2. And let's suppose we start with an initial condition. And we could interpret this. Remember, x1 is our predator. So maybe this is saying our initial population of predators. And you don't have to necessarily think of it as just 2 wolves. Maybe that 2 means 200 wolves, right? Maybe we're just making the number smaller. And similarly, maybe our initial deer population is 400, right? So now, one thing you'll notice about this, you don't have to do this, but I think the more you can attach some meaning to these differential equations, the better you're going to understand them. And that's why I like the analogy of the predator and the prey. Note that for my first differential equation, this is talking about the predator, if we'd happen to not have any prey, like if x2 was 0, if this term was 0, then what is this saying about our predator population? Recall that when we see a differential equation like this is describing exponential decay. Remember our first problem, dx dt equals ax. Here my a would be negative. So this would be a decay. Now, that makes sense to me, right? If there's no prey for the wolves to feed on, they're going to die off, right? Similarly, if we think about the deer population differential equation, if there were no predators, right? If x1 was 0 in that differential equation, then we would just be left with dx2 equals 4x2. Now, what is that describing? Just like this, but this time it's positive, that would say that our deer population would grow exponentially. That makes sense to me too, right? If there's no predators hunting the deer, then the deer population will thrive and they're going to grow exponentially. So I hope you can see that, there's some meaning behind these variables in that this is a reasonable set of differential equations to model a predator-prey population. Now, what we want to see happen is what's going to happen long term. So here's the math part. This particular linear system we're going to write in matrix form. So we could think of the two differential parts here as one matrix, or oftentimes when it's a column matrix, we'll call that a vector. And this gets a little confusing, but that will get denoted dx bar dt. The bar means a vector. That means we're talking about more than one thing. That's my coefficient matrix times x1, x2. Remember how you multiply matrices? You go row times column. So this could be read as dx1 dt equals negative x1 plus 2x2. dx2 dt is negative 3x1 plus 4x2. Now we can condense this down to dx bar dt equals a. Remember, we usually use capital A for a matrix, and we'll combine x1 and x2 as a vector, x bar. Now the idea behind the solution goes back to our very first example. We saw that when we had a differential equation of the form dx dt equals little a, being a constant x, the solution was ce to the at, where a was a constant. So it kind of makes sense that if I have, notice the similarity, right? If I have dx bar dt equals capital A times x, then the solution would be x bar equals ce to the at. Now there's a big, huge difference here, right? It makes sense to have a constant times t, but it does not make a whole lot of sense to have a matrix times t. Okay, so we can't have matrix A as an exponent. But what did we learn? Matrix A can be replaced with its two eigenvalues. Remember, think about the definition of an eigenvalue. An eigenvalue can take the place of a matrix. So what happens then is that solution we just suggested, we modify it. Generally speaking, a 2x2 matrix will have two eigenvalues. So we can write this as C1e. We can replace A with lambda 1t times its eigenvector. But there's another eigenvalue too, right? So we would want to include that as well. C2e to the lambda 2t times its eigenvector. And we do, it's a sum of these two. And C1 and C2 are going to be constants that we can solve for later. And that is going to be our general solution. We're going to use this solution over and over and over and over. Now, fortunately, if you go back to page 2, we already found the eigenvalues and eigenvectors. I used the same matrix. So that means our general solution is going to be C1e. Remember, one of the eigenvalues was 1, and the corresponding eigenvector was 1, 1. So ce to the t times 1, 1, plus c2e to the 2t times 2, 3. That was my other eigenvector and its corresponding eigenvalue. Now, what we'd want to do is solve for those constants by plugging in the initial conditions. x1 of 0 was 2, x2 of 0 was 4. So I can, okay, notation, you could say x bar of 0, but remember that really means both of these. is C1. Now T is 0, so I'm plugging in 0 for T. So lambda times 0 would be 0 times its eigenvector. And same thing here. This was e to the 2t, but if t is 0, that's going to be 1. Now there's two equations here. x1 of 0 is 2, x2 of 0 is 4. So if I read the top row, 2 would have to equal c1 times 1 plus c2 times 2. And 4 would have to equal c1 times 1 plus c2 times 3. So I get a system of two equations. You know how to solve this. You can solve it any way you want, by elimination or by solving for c1 and plugging it into the other. Either case, you're going to get c1 is -2 and c2 is 2. So our particular solution, if I put c1 and c2 back in, x bar of t, -2 e to the t times 1, 1, 2 e to the 2t times 2, 3. Now, what we really are wanting to be interested in, remember we put context here. X1 is our predator population, X2 is our prey population. And what we want to know is what's going to happen long term. So in other words, as t goes to infinity, if I take my top solution for x1 of t, well, this is going to get infinitely big, right? And this is, if I plug in infinity here, that's going to be even bigger, right? Because it's 2 times infinity rather than just infinity. So even though this term, you could argue, goes to negative infinity because there's a negative in front, this is a bigger infinity. It's going to overpower that negative infinity. So this would go to infinity. And for the prey population, there's same idea, right? If t goes to infinity, that goes to negative infinity, but this is a larger infinity. Okay, so they'll both approach infinity. So they both thrive, right? Now, the next page, we're going to talk about all of this can be visualized in what we call a direction field. And a direction field is a set of vectors that we can use, that we can generate without even solving the differential equation. This comes from the actual problem itself, and it gives what we call solution trajectories. Let me show you what this looks like. Okay, this is a computer-generated one. We can talk about ways coming up in future videos here where we can generate this ourselves. Okay. Now, we'll have to talk about in the next video, we'll have to talk about what we mean by an equilibrium. And the equilibrium for all of these linear systems is going to be 0, 0. And that's just because if there's no predator and there's no prey, there will never be any more predators or prey, and that's going to always stay the same, okay? You may recall the idea of a fixed point back in when we were studying recursive sequences. It's kind of the same idea. Now, what you're seeing is a bunch of arrows, and you can see the numbers down here. This is the X1. This is our predator population. This is our prey population. And what these arrows, they're generated from the differential equations, but you can use these to kind of model what was going to happen. Recall, our initial solution had our initial wolf population being 2 and our initial deer population being 4. So I'm going to narrow in on this. And recall what we found happen was both the deer and the wolf population would go to infinity. If you follow the arrows, you can see that this solution trajectory is going to take me upwards and away. So my predator population, which is X, will go to infinity, and my deer population, which is Y, will go to infinity. What you can also hopefully see, though, is that depending on my initial condition, if we had started this problem with an initial condition of 3 wolves and 2 deer, what we would have seen is our solution, our deer population would have gone up a little bit, and then it would have quickly gone down. Now, the full solution takes me down here, but if you think in reality, in real terms, by the time we get right here, we have a positive wolf population, a positive predator population, but my deer population is now at 0. So the deer population is now extinct. The wolves have won out, okay? But now they're in trouble because there's no more deer. Some of these other trajectories you can also imagine, they don't make much sense in our context because we have a negative predator population, you know, so, but anyhow. Okay, more about that equilibrium. An equilibrium, also called a steady state, for all of our linear, homogeneous differential equations, homogeneous just means that if your differential equation has an x1 and an x2 and no other numbers, there's nothing else added. If you set these equal to 0, because equilibrium implies no change, no rate of change, the only solution that will solve both of these is having x1 and x2 both be 0. So when I set up in the direction field that the equilibrium is 0, 0, that's how you find it. You set your differential equations both equal to 0. Okay, and then finally, you can tell from those solution curves that any initial condition will take you away from the equilibrium, right? All of these solution curves point away from my equilibrium. They go away. And so this, we classify that equilibrium, it's called an unstable node, also called a source. The image I like to think about in my head, if you've ever seen a natural spring in the wild, a spring of water where water is bubbling out of the ground, we often call that a source. It's a water source. And I kind of think of these arrows as they're bubbling out here and they're going away from 0, 0. Okay, so that's where that name source, or that's the way I like to think of it anyhow. Also an unstable node. And we'll see that the equilibrium 0, 0, there's different classifications for what can happen. This is just one of them, and we're going to have more videos on how we classify the equilibrium. Okay.